Our next step in the analysis was to determine the activation energy of this particular failure mode. Again, we utilized ReliaSoft software, in this particular case Alta software, to determine the activation energy for this particular failure mode. In this case, we have the field data, which was run at 50 degrees C. Then we have accelerated live test data that was run at 150 degrees C. Again, based off of the literature review that we performed, we found that the industry acceptable model to look at activation energy and acceleration factors is the Arrhenius model. So therefore, we implemented the Arrhenius model in Alta and determined the activation energy for each case. In the case of the unscreened data, we found that the activation energy is 1.28. In the case of the screen data, we found that the activation energy is 1.22. This is quite interesting and surprising to us. Well, not so much surprising to us, but confirms some suspicions that we had that this particular data set from company XYZ does not demonstrate intrinsic type failure modes for data retention. Since the activation energy during our literature review was 0.6 EV, and we see here from the actual field data for both populations that the activation energy is doubled. So what we're seeing here is that the data that we're analyzing is not behaving as expected. That's what we're drawing from this particular analysis, that something else is going on. There is a much stronger failure mode present than one that is intrinsic to NOR flash. The next section that we will cover is the application of results. We are again looking at the unscreened data with an acceleration factor of 477.08, T50 of 4.9987. In terms of the screen data, we have an acceleration factor of 371.29, T50 of 1.5078. Again, using the Arrhenius equation, which is displayed here, along with the two temperature sets, T1 at 323.16 kelvins, T2 at 373.16 kelvins, and again, we are assuming that there are no failures for the normal product. Since it is a defect subpopulation, we find that F is equal to P times FD. F is equal to PFD. So the unscreened data, the FD for 20,000 hours is equal to 9.48 to the negative 544. And basically F is 0.007. For the screen data, we find that F is 0.005735. So what was leading us to, our analysis is leading us to, is that a burn-in screen is not really doable here. Not due to cost or equipment roadblocks, but rather a time frame, because the nature of the failure is prohibiting us from truly screening out all of the failures in a time-efficient manner. So that, since knowing the acceleration factors and the burn-in time that of basically 1,000 hours allows us to determine the equation for burn-in to calculate the failure rate. So for the unscreened scenario, we have a failure rate burn-in time equal to 0 for both cases. So then again, this leads us to the belief that a screening time, an efficient screening time, and time-efficient, cost-effective for a company to implement, is not present in this particular case. So it leads us to our conclusions here. Our conclusions here are that our parameter estimation shows a high rate of early life failures. Basically, since our standard deviation is greater than 2, this leads us to believe that there's a high rate of early failures. The failure mode is not intrinsic. Again, the intrinsic activation energy for data retention is 0.6 based on our literature review. and the activation that we're seeing through Alta is twice as large for both cases. Therefore, the filled population cannot be screened. The failure mode needs to be eliminated for company XYZ to move on doing business as usual. So what do we suggest? Our suggestions are to basically go through a corrective action process, again, to eliminate the bit flip failure mode from occurring. They need to modify the mask set during the wafer fab to protect the NOR flash gates from the ion implantation steps that are needed for other devices within the controller chip. Basically modifying the mask from what it is on the left image that we have here, showing that the NOR flash area is unprotected during the ion implantation step, again affecting the oxide of the NOR flash. What needs to take place is basically a blocking mask needs to be implemented, again preventing damage from occurring during the ion implantation stage. With that, we conclude our presentation, and thank you all for spending time to listen to us.